Hey everybody, welcome back to another RevWise video. I got a comment in the last video and requested the chemistry higher level paper 2. We did the standard level paper 2. Now we wanted the higher level paper 2. So of course we're gonna get right on that today. Haven't seen much of this paper, but some of the questions are the same as standard level paper, so I'll just breeze over them. If you want the detailed explanation of those questions, please refer to the standard level video for that. But yeah, let's just go right into it, see how we do. Okay, so this I'm pretty sure is the same as standard level 1. Let me check out. Yeah, so there's an additional part to it, so I'll just complete it quickly, this first part, and then I'll talk about the additional part later. So I mean, if you're at higher level, this should be like something you do in 2 seconds, right? You're just taking the percentages, using them as your mass. I'll just do it for carbon to show you an example. So you're basically using that as your mass and then putting that over the molar mass for each of them, so it's 12.01. For hydrogen, you'd be doing that over 1.01, oxygen over that over 16, of course, and you get 3.33 moles, 6.66, and 3.33, and that gives you CH2O, right? Again, if you want detailed explanation, if you don't understand this, just refer to the standard level video, but I'll just explain it quickly. Okay, B, 25 cm cubed of solution containing 1.51 grams of HX is titrated with 0.75 mole dm cubed solution of NaOH. The HX solution is exactly neutralized by 22.3 centimeters cubed of the NaOH solution. Determine the molar mass of HX. Okay, for this, we know that it's titrated exactly, and we know the ratio is going to be 1:1. And we have 22.3 cm cubed with a concentration of 0.75 mole per dm cubed. So it's essentially 0.75 times 22.3. Remember, we have to make it dm cubed. So we divide it by 1,000, and that gives us a value of 0.0167 moles. Okay, and that's our moles, and then we have the mass of HX. So what do? We do mass 5.1 over the moles, 0.167, and that gives us a molar mass of 90.4 grams per mole. Lovely. Molecular formula of HX. So for molecular formula, we're just looking at what we get when we add all the mass numbers for our empirical formula. Let's do that first. So we'll just do it roughly. So it's like 12 plus 16 plus 2, yeah, so that's 18 plus 2, 30, and since it's roughly 30 for our empirical formula, and we know that our molar mass is 90, we know the molecular formula is going to be 3 times whatever the subscript numbers are. So the way we got 3 is by doing 90 over 30, which we got from adding up the things from before, and that gives us 3. So what do we do with the 3? We just basically multiply each of the subscript in our first one by 3. So it's C3H6O3. Lovely. HX reacts with aqueous sodium hydroxide according to the equation, sure. And it wants us to identify functional group. Well, we know that it's reacting with aqueous sodium hydroxide and it's forming this NaX and H2O. So we should be able to identify it's going to have some sort of carboxyl group because it's acting as an acid. So we can say that there will be a carboxyl group. Yeah, COOH. Okay, identify the functional groups responsible for the absorption bands shown at Y and Z using section 20 of the data booklet. Okay, so we have what wave number? So Y is at roughly 3,500. Z is at let's just say 2,000. Yeah, just under 2,000. It's like 1,700. Yeah. So let's have a look at our data booklet. Section. Again, I wonder if I can rotate this. I wasn't able to do it last time. I think we'll just leave it as it is. Okay, so we saw it was like 2,500 and 3,500 and 1,700. So 3,500, it kind of corresponds to this. 1,700 It's corresponding to this one. Okay, so we found them. So the 3500 one is OH in alcohols. OH. Yeah, so hydroxyl group. And then this one is C double bond O. This is a carbonyl group, but it's referring to the one in carboxylic acids, right? We know that because of our previous answer to the last question. But basically, you can see that it's C double bond O is a carbonyl, but it can be from aldehydes, ketones, esters, right? But this one corresponds to carboxylic acids. Okay, so draw a structural formula of HX that is consistent with all the evidence. So we know it'll have this carboxyl group. We know that it'll have this C3H6 O3, and we know that it has well, we already said it has a carboxyl group, right? Because that's comprised by this carbonyl and by this so it'll have this carboxyl group and it'll have a hydroxyl group as well. So how do we draw that? Well, we'll draw our central carbon. We know that it'll have a carbon on either side. And then we know that at least one of the carbons will have this will be the carboxyl group, right? So this can be that for us. I'm going to draw it like this to give you the idea, but I'll show you how you can draw like something that's more consistent with what a structural formula actually is. But yeah, this works as well. There we go. So this is our carboxyl side, so we've checked that off. Okay, so if you think about it, we've checked this part off. Now we need to check off this, because this corresponds to the same things, but we need to check off this part, the hydroxyl. So that can be just put that on the central carbon. So we have that hydroxyl, and then we have our H, and then we can just finish this off with a CH3. And if we check for our things here, we have H6, C3, O3. And when we check our small molecular formula, it corresponds to the molecular formula. So it's pretty simple. Another way to just write it, once you have this visualized, you can write it like this. Another way, it also works, just different ways you could have done it. Yeah, as long as it matches with that, as long as your structure matches with the information you're given, don't worry about it. Pretty simple question. Question 2 is this one, Rutherford Gould question. We answered this in the standard level video. I'll give brief explanations on this, but again, if you want the real explanation, please just refer to the standard level video. So this one is just showing how an alpha particle is a helium-formed nucleus, and in an experiment, they're accelerated towards this sheet of gold, and the resulting paths are detected. And it's telling us that this gives evidence of the positive charge of the nucleus, and then we have the experiment detailed here. And we'll just explain the experiment as we go with the questions. So explain why some alpha particles follow path 2, rebounding from the gold sheet. Well, here you can see that path 2 is this one right here. So it's hitting the gold and it's going backwards, right? And so it tells you in a later question, but I'll basically spoil it for you. Majority of the particles are following this straight path, right? Only a few of them are rebounding. And the reason for this is because, I'll explain the reason in a later question, but essentially, these path 2 are rebounding because there is a repulsion force, right? But where can this repelling force come from? Well, if you think about a sheet of gold, right? If you think about the gold atom, you have something in the middle, right? Something in the middle. What is that, right? This is the atom, right? Very basic structure. Yeah, something in the middle. That is your nucleus. It is filled with protons, and it's a positively charged. Now, that positive charge repels the likewise positive charge of this alpha particle. So when you shoot an alpha particle, which is positive, at a positive nucleus, it's going to repel. So, yeah, it's essentially repelled by the positive charge of the nucleus. Okay, most of the part alpha particles follow path 1. That's what I said before, yeah? And pass straight through undeflected, which is at a 0 degree angle. And what conclusion can we draw from that? Well, if most of the particles, remember these particles just randomly fire towards the sheet of gold, right? And most of them are going through here, right? We know that it's not going there because we're aiming there, right? It's just random. So what can we deduce about the structure of the atom? Well, we can deduce that this nucleus, right, is actually a lot smaller than we think. It actually only takes up a very small portion of the atom. And that's why a lot of them are passing at 0%, 0%, 0 degree angle. So our conclusion is the atom is mostly empty space. Okay, outline the appearance of the emission spectrum of helium. So emission spectrum is just discrete lines of different frequency. It's just a definition question. You should be able to remember that. Okay, and emission spectra of one electron systems can be explained by using a model with the electron attached to the nucleus by an electrostatic force. This model predicts that the electron occupies discrete energy levels. Some levels for the helium-ion are shown. Explain how the frequencies support the idea of electrons occupying discrete energy levels. So it's asking us to explain how how the frequencies observed in the emission spectra, how they support this idea of having these discrete n equals 1, n equals 2, n equals 3. How does that work? Well, the energy of a photon corresponds to a frequency, right, in the spectrum. So in the spectrum we have frequencies, and the energy of a photon, each energy is going to correspond to a frequency, right? And the energy is dependent on the difference in energy levels, right? You can see that the difference in energy levels is what the actual energy value that we're getting is dependent on, and each energy it corresponds to a different frequency on our spectra, and that's how it essentially shows that each electron is occupying these distinct levels, because they are the frequency is which gives us the energy is dependent on these energy levels. When we're assigning these energy levels, it's dependent on them, and that's what's hence proving the idea that we have these distinct n equals 1, n equals 2, and there's this difference between them that converge at higher frequencies. So yeah, deduce the ionization energy of the helium-ion from the energy levels shown. Well, yeah, so we can see that this energy here, minus of 5250, that's at n equals 1. So if you think ionization energy, we are essentially going the opposite direction. We're getting like that. So it would be 5250 kilojoules per mole. Okay, now we have to suggest 2 reasons why the ionization energy of the hydrogen atom is significantly smaller than the ionization energy of the helium ion. Oh, this is pretty simple. So it's trying to draw a structural similarity between them, because the helium ion, when you're moving it, it's looking quite similar to the hydrogen atom, but there's still clear distinctions, right? So distinction number 1, right? The helium ion, even though it's a helium ion, it's still, as you can see in our periodic table, we can see that it has this 2 atomic number, whereas hydrogen has 1. What does that mean? That means that hydrogen has half the number of protons, hence half the nuclear charge. And what else does this mean? Well, we know that helium is an ion, right? And due to it being an ion, the ratio of protons that it has in the nucleus to the electrons in outside is higher. Essentially, there'll be a stronger pull, and that means that its ionic radius is going to be quite small, and definitely smaller than the hydrogen atom. So what does that mean? It means that hydrogen has a larger radius, right? Larger radius. We all know how that corresponds to ionization energy, right? Just remember that helium is an ion here, and that pull from the nucleus is pulling the electrons inside. It's a smaller radius. Suggest why the model outlined in BII can predict the emission spectrum of helium ion but not helium atom. This is quite simple. It's quite it's just a piece of theory you have to know. So when we have the helium atom, we have to take into account electron repulsion. Repulsion must be taken into account, right? When we have helium atom, we'll have this pair of electrons, and then that's going to cause interactions between electron repulsion, and then when taking that into account makes everything more complicated, and then this model can't predict the emission spectrum anymore because of this. All right, outline my models of the atom have evolved over time. Very simple. I've answered this whole question in the SL. I don't know why I did it again, but oh well. So there's oh my gosh, new evidence. One reason. What else? New technology. Can't believe this is an actual question they put in the paper. This isn't even. I don't even think this is chemistry. This is more like just logic. Develop related model. These are a couple of things they want you to say, but realistically, you say anything plausible here, they'll give you the mark. Like I'm sure they'll give you the mark if you say anything plausible. Okay. Oh, this seems to be a new question. Lovely. Okay, let's try this. The development of the lithium-ion battery won the 2019 Chemistry Nobel Prize. The diagram represents a cell in such a battery delivering a current. Complete the half equations on the diagram and identify the species moving between the electrodes. So, okay. So we have just a lithium. This is quite a cool question, actually. Okay, so this half equation, how do we complete it? Well, we can see that this LiCOO2 is being converted to 2 LiCOO2. So we're clearly we're getting a lithium, right? Yeah, that's what we're getting, because this already has this 2 subscript here, which means there's 2 of each of these. So we're getting a lithium. Getting that lithium, we're also going to be getting an electron. That's probably why they went as a half equation. So it should be this Li plus, and we'll have to compensate with the E minus. Okay, so that's our half equation. Now, what species is moving? So we have the cathode and we have the anode, and we have. So this is electron flow, and this is the one that's moving from the anode to the cathode. So from the anode to the cathode, it's going to be our lithium, this species, positive lithium ion, so Li plus. Remember, I don't think they'll give it to you if you just write lithium. So yeah, don't do that. And what does it want at the anode? It wants us to write the half equation. Okay, so half equation, we're just going to be doing the opposite. So Li forms Li plus E minus. And yeah, that looks about right. The discharge of the lithium-ion battery is a spontaneous chemical reaction producing a potential difference and an increase in temperature. Deduce the signs of the following. So the delta H of the discharge is spontaneous, right? It's spontaneous, and we know that it produces a potential difference and an increase in temperature. So that's all the information that we need to get this answer. So what's the first thing that what's the first piece of information that we get? We get that it's spontaneous, right? That already gives us the delta G sign. Remember, delta G for spontaneous reactions is negative, so negative. Okay, what else do we see? Well, we know it produces a potential difference, and we know that it causes an increase in temperature. So from that, we know that our delta H for discharge is also going to be negative because it's going to be an exothermic reaction, hence the increase in temperature. We know it would be a decrease if it's endothermic. And then, I mean, even from these two, we should be able to find the E cell, but from the question, we should know that the E cell is going to be positive. There we go. And we can test this combination by seeing what this gives us, but